Hello everyone, I am Susanta from West Bengal. I have completed my bachelor's degree from Mednapur College Autonomous. Today I am going to share my interview experience at ICTS-TIFR Bangalore. I was shortlisted through the GS examination conducted by TIFR in December. In this video, I am going to share you uh, what the interview was like and the kind of questions I was asked. So, on the day of my interview, after document verification, uh, I was called into the room, and there are two professors uh, on my panel. They started with a very simple question that what are the topics I'm most comfortable with. So I replied quantum mechanics, electromagnetic theory, and thermo and statistical mechanics. So they gave me a problem that that I'll show you on the screen. I have so the first question they gave me is this. So there are four fixed point charges of equal magnitude plus q are placed at the corner of a square of side A. So uh, there are four plus q charges, okay, of equal magnitude and obviously same mass. So they are placed at the center of the corner. Sorry, they are placed at the corners of a square of side A, and a fifth point charge of magnitude minus q is placed at the center of that square and is allowed to move only along the x direction perpendicular to the plane of the square. Okay, so the question is actually there are four plus q charges situated at the corners of this square, and a minus q charge can only allowed to move along the perpendicular to this plane, and it can move only on this direction, and this direction is called something x-axis. Okay, now the question is find the classical partition function of this system at temperature T. Okay, so I have to find the classical partition function for this system at temperature T. Now uh, we know that the classical partition function Z is equal to 1 by h integral e to the power minus beta h. H is something function of momentum and generalized coordinate, and dp dq. Okay, now this is the system, this is the figure of this system we have, and we have to write the Hamiltonian for this system. Okay, now this minus q charge can move only in this direction, which is called x-axis in this problem, and we have to write the Hamiltonian, and this is the partition function, or I can say this is the classical partition function for 1 degrees of freedom, because here is only 1 degrees of freedom of this system. Okay, now so I can write this q as only x. I can write this momentum as px, and this generalized coordinate as x. So this is the Hamiltonian, the function of Hamiltonian. Now I have to write this Hamiltonian of the system. So Hamiltonian of the system H is equal to, so I consider this as a conservative system. So H is equal to T plus B. So T is equal to that kinetic energy of the system. So this particle can move only in x direction, so it can have only px momentum. So this is equal to px square by 2m. This is the kinetic energy of this system plus potential energy here. Okay. Now I have to write the potential energy of this system. Okay. Now for potential energy, so we know this length. This length is something. This length is a by root 2, and this is something x, and I call it, this is r. So we know the r is equal to under root of x square plus a square by 2, x square by a square by 2, and the potential energy of the system, and that is actually electrostatic potential energy of the system, Vx is equal to minus minus k q square by r, and this for this 4 charges, there is 4, because we have to write the total potential energy of the system. Okay, the interaction between this and this, this and this, this and this and this charge. So I have to multiply 4 with this potential energy. Okay, now this is equal to minus 4 k q square divided by that r is equal to under root of x square plus a square by 2. Okay, so this is my potential energy. Now I can write the Hamiltonian of the system. Okay, now this Hamiltonian of the system is something like px square by 2m. Okay, plus, and I have to write this potential energy is equal to minus 4 kq square by under root of x square plus a square by 2. Okay, now this k is equal to this k is actually 1 by 4 pi epsilon naught. Okay, okay. Now this is the Hamiltonian of this system. Now I can write the partition function. Okay, just this. Okay. Now the partition function z is equal to 1 by h integral e to the power minus beta. Now we all know that beta is equal to 1 by kb into t, where kb is Boltzmann constant and t is the temperature at which the system is. Now beta is equal to 1 by kb into t, and that Hamiltonian is nothing but px square by 2m minus 4kq square divided by under root of x square plus a square by 2, and dpx dx. Now this is equal to 1 by h integral e to the power minus beta by 2m and px square dpx and integral e to the power 4 k beta q square divided by under root of x square plus a square by 2. Okay, and dx. Now, then one of the professor uh, told me that if you solve this integral, you can get the answer. So uh, you don't have to calculate this integral. Now they skip to next question. The next question is
Okay, this is the next question. If minus q charge is displaced slightly along the x-axis, what is the frequency of its oscillation? Okay, now in this figure, we'll see that when we displace this minus q charge from the center of the square slightly, okay, it was actually attracted by these four charges, okay, so
it moves like this and goes like this, and it moves in a twin flow motion and actually execute a simple harmonic motion. Okay, so this is the potential energy we have for this system. Okay, and we know the force is equal to minus dv dx. Okay, now if we do derivative of this potential, we can get the force. So we have uh, uh, this potential energy and derivative of this, and we get this answer. Okay, so uh, so here we assume that this displacement is very small displacement, means this x square is much smaller than the side length of the square. So if we approximate this thing, so we will get this answer. Okay, so and we all know this, and force is equal to minus m omega square x, and from there we can calculate the angular frequency. Okay, so if we calculate the angular frequency, we can get the frequency of oscillation, that f is equal to omega by 2 pi, and we also can get the time period of this oscillation. Okay, so this was my second question, and then the next question was plot the graph of the electrostatic potential for this system. The electrostatic potential was Vx is equal to minus 4kq square minus 4kq square divided by under root of x square plus a square by 2, under root of x square plus a square by 2. Okay, minus 4kq square divided by x square plus a square by 2. So this was the potential energy we have. So I have to plot the graph of the electrostatic potential energy for this system. Okay, so just draw the axis, and we have in this direction x, and this is dx. Okay, now I will check the behavior of this kind of potential for each point, or I can say for very specific points, like what is the behavior of this potential at origin, or at infinity, plus infinity and minus infinity. So I'll go ahead. So when x is equal to 0, the potential V at 0 is equal to, when I put 0 in this equation, that is equal to minus 4kq square divided by, when x equal to 0, that will give a by root 2. So this is actually minus 4 root 2 kq square divided by a. So we get that at x equal to 0, it has some negative value. Okay, so let's say this. Now when x tends to plus minus infinity, so when x tends to plus minus infinity, the denominator goes infinity and the potential goes to 0, but 0 minus. Okay. Yes. Okay. I think the graph of this type of potential is something like this. Okay. This is the graph of this type of potential, and this point is actually 0, and this potential is minus 4 root 2 k q square divided by a. Okay. Yes, this is the graph of this electrostatic potential. Okay. The next question is, write down the classical and quantum mechanical energy eigenvalues for this system. Also write the null point energy. Okay. Now for a classical system, we also derive this actually. Uh, uh, the Hamiltonian, classical Hamiltonian H is equal to Ex square by 2m, and that minus potential energy minus 4k q square, minus 4k q square divided by under root of x square plus a square by 2. Yes, it is this. So you can take any value of position and momentum. So it can take any value, any energy eigenvalue in classical. So in classical, it can take any value from minus infinity to plus infinity. Okay, so this is the classical Hamiltonian, and if I consider this system as a quantum system, or like I mean that if we approximate this system as a one-dimensional quantum harmonic oscillator, so this is for small displacement. Okay, so for small displacement, we can approximate this system as a quantum one-dimensional quantum harmonic oscillator, and for that one-dimensional quantum harmonic oscillator, we know the result of the energy eigenvalue, that energy eigenvalue En is something n plus half and h cut omega. So okay, so those are the energy eigenvalues for n is equal to 0, 1, 2, 3 and so on. Okay, so if we put the values of n, we get discrete values of energy. So for quantum for this system, if we consider this system as a quantum harmonic oscillator, so we get discrete values of energy, and also write the null point energy. If I want the null point energy, that is the lowest energy. That lowest energy is for n is equal to 0. For n is equal to 0, that is E0 is equal to half h cut omega, and that is equal to half h cut, and we have the omega from from this. We have also calculated this. Okay, so this is the omega. We have this. This is actually the frequency of oscillation, for slightly, or I can say this is for small displacement. Okay, so for small displacement, I can approximate this system as a one-dimensional harmonic oscillator. So actually, you can see this as by this graph. So I can assume this, or I can approximate this thing for lower value of energy. So this is a quantum harmonic oscillator for lower value of gain, or I can say lower value of energy. So this, and that omega is under root of 4 k q square 2 to the power 3 by 2 divided by m a q. Okay. Now this is the null point energy. Now moving to next question. Now what is the bound state, and in this problem up to which energy the particle is bounded. Now if we want the bound state, what is the bound state? Now I'll draw the same graph again, that something kind of this. Okay, this is x and this is Vx. Now what is bound state? When the energy of that particle, or I can say that system, is lower than the potential energy, or I can say uh, if this is the potential profile of this potential energy profile of this type of system. So if the energy is something like this, then it is bounded, or I can say this is the bounded particle. Okay. Now, what is bound state? So this is actually the this particle is bounded over this potential uh, potential well actually. So, and up to which energy the particle is bounded. So actually the answer of this question is when energy is less than zero. Energy is less than zero, the particle is bounded, and when energy greater than equal to zero, particle is unbounded. Okay, or I can say this is the bounded state and this is the scattering state of the system. Now the last question of this section is give an example for a system where the low energy states are discrete and the high energy states forms a continuum. So here you can see that this is a bound state. Here the particles have discrete energy states, and when we goes the greater energy, the spacing between the energy levels decreases, and after some energy levels, or I can say uh, after uh, energy level, so it will something continue, not discrete. Okay, so that type of example we have already mm, we have all this type of example like hydrogen atom. Okay, so in hydrogen atom we can see this, the low energy states are discrete, and when it goes higher energy levels, the spacing between two energy levels are decreases, and and form a continuum. Okay, the energy states form a continuum. Okay. Now the another professor asked me the next question. and that question was how you can estimate the mass of the sun. So I told him that I can use the Newton's law of gravitation to estimate the mass of the sun. And how, let's say this is our sun, this is our sun, and a planet, let's say Earth, revolves around the sun in a circular orbit. Okay, so in a circular orbit, let's say this is my Earth, and let the mass of the sun is capital M, and the mass of the Earth is small m, and the distance between sun and Earth is, let's say, r, smaller. And we know to stay in a circular orbit for any object, here it is a planet, Earth. So they required a centripetal force, and the gravitational attraction force between them, that force actually provides the required centripetal force in this case. Okay. Now I can write that the gravitational interaction force between them is something G, mass of the sun, and mass of the earth divided by the distance between them is something r, square of this distance, and that provides the centripetal force, and that is equal to m v square by r. So now from here we can get this. So this will goes this. So the mass of the sun, capital M, is something is equal to this r v square divided by g. Now we know that this earth revolves around the sun, and the time period of this revolution t is equal to 2 pi r by v. Now from here we can calculate the v, velocity of this earth. V is equal to 2 pi r by t. Now here you can write that r by g, and this is 2 pi r divided by that t, and square of this. So this is equal to 4 pi square, and this is r cube, and divided by g t square. Okay, so this is the mass of the sun. Now we know the distance between distance between sun and earth, and we also know the time period of revolution, that is 1 year 365 days. So t is equal to 365 days, and we also know the value of g. So from here we can estimate the mass of the sun. So the next question is, now plot the graph between the velocity of any planet and its distance from the sun. So we have already derived this expression for velocity and velocity of any planet and distance from the sun from the concept where the gravitational force provides the centripetal acceleration, that g m by r square is equal to m v square by r. So from here that v is equal to that v is velocity of any planet, that v is equal to under root of g m by r. Now we can plot the graph of this okay. So in this axis, this is r and this is the velocity, and we can get that velocity is proportional to 1 by root r, and the graph of this is something kind of this. Okay. So yes, this is the graph between velocity and distance between that planet and the sun. Okay, so actually this velocity decreases when the distance between the planet and the sun increases. Okay, now the next question was a star orbits the a star orbits the center of a galaxy with constant speed, and what kind of gravitational potential does it experience? So this is actually a question from astrophysics, that where the professors told me that that in a galaxy, stars are distributed over the galaxy, and at some radius r, so some kind of distribution are there, and after that particular distance, so this mass distribution decreases, and and the main thing is uh, in this galaxy that star actually have a constant speed. Okay, so uh, let's say this is a galaxy, and there was a random distribution of mass of stars was there, and we just have to calculate the gravitational potential, that okay, the gravitational potential it experience. Okay, for this we know that if any star, let's say this is the star and this is the center of that galaxy, and this uh, revolves, or I can say orbits the center of galaxy with a constant speed. Okay, with a constant speed, and the thing is, for revolution of this planet, it should have the centripetal force. That centripetal force provides by the gravitational acceleration, that gravitational force, and that force is actually F is equal to m v square by r, and we also know that F is equal to minus grad v, or I can say this is minus dv dr. Okay, now from here this is equal to Vp. This V is actually the potential, the gravitational potential it experiences, and this V is actually the velocity of this star. Okay, now this is equal to minus mv square dr by r. Now we have to integrate this thing. Okay, now this is equal to v, and that is equal to minus mv square, and this is ln r plus something integration constant c, and this is a expression for gravitational potential heat experience. Okay, now thank you. So that are the questions I was asked, and thanks to all of you. And I hope this video will help you and for your upcoming examinations, also for interviews. And thanks to Sotto sir to give me an opportunity to share my interview experience. Okay, thank you.